Welcome to the deep dive. Today, we're really getting into ratio and proportion.
Yes, we are.
You've shared this great chapter, looks like from a math textbook, and it's just packed. Definitions, properties, loads of examples.
It is.
So our mission today, I think, is to unpack these ideas, make them clear, engaging, and really get the logic behind them,
Exactly. They seem basic, maybe, but ratios and proportions, they're sort of the hidden language behind, well, so many comparisons we make every single day. Scales, relationships. It's about understanding how things fundamentally relate.
Okay, let's dive in then. Start right at the beginning. What is a ratio in its simplest terms?
Right. So at its heart, a ratio is just comparing two quantities, but they have to be of the same kind and in the same units.
Okay.
The textbook puts it as dividing the first by the second. So A and B, the ratio is A divided by B, or we write it a colon B, AB.
Good.
And crucially, that second term, B, it can't be zero. You can't divide by zero.
Right, basic rule. So it's purely how much of one thing versus another.
Exactly. A direct comparison.
And the book points out some key things about ratios. First, they don't have units.
Yeah, that's important. If you compare, say, 10 kilograms to 5 kilograms, the kilograms cancel out.
Ah, okay.
They're left with just 10.5 or simplified 2.1. It's just the number relationship.
Makes sense. You're comparing like with like.
Precisely. And another big one, order matters. A lot.
Oh, yeah.
Yeah, AB is usually totally different from BA, unless, A and B are the same number, then it doesn't matter. But otherwise, it changes the whole comparison.
Totally. Like saying twice as many versus half as many. Same numbers, different story.
Exactly.
The text also mentions multiplying or dividing both parts by the same non-zero number doesn't change the ratio itself.
Yes, this is key. It's like equivalent fractions, right? 1 over 2 is the same value as 2 over 4 or 5 over 10. It lets us simplify. We always want to get a ratio down to its simplest form. That's when the two numbers are coprime.
Coprime, meaning they don't share any common factors except one.
That's it. So like 3.7, that's already in its lowest terms, but something like, say, 4.12.
You can divide both by 4.
Right. You get 1.5. Same relationship, just simpler.
Okay, simplify. Got it. Now, the textbook throws us some examples. This is where it gets practical.
Yeah, let's look at one.
There's one where it gives this ratio, 2x plus 3y, compared to 3x plus 5y equals 18 compared to 29. So 2x plus 3y, 3x plus 5y, equals 18.29. And we need to find xy. How do you even start with that?
Well, it looks complicated, but it uses that core property of equal ratios, like equal fractions. You cross-multiply.
Ah, okay. So 29 times the first part equals 18 times the second part.
Exactly. 29 2x plus 3y equals 18 3x plus 5y. Then it's just algebra. You expand the brackets.
Multiply everything out.
Get all the x terms on one side, all the y terms on the other. And when you simplify all that down, you isolate the x and y relationship.
And it turns out
that x point y is 3.4. It's quite neat how algebra just pulls that ratio out.
that is pretty neat. Okay, another one. This time we know xy is 2.3. We need to find the value of 3x plus 2y, 2x plus 5y.
Right. And the book actually shows a couple of ways to do this.
Yeah.
One way is you can divide the top and bottom of that second ratio expression by y. Since you know xy, you can substitute that value in.
Sure.
Or another way, maybe more intuitive for some, is to think with a common multiple. If xy is 2.3, then x could be, say, 2k and y could be 3k for some number k.
Ah, right. Using a placeholder.
Yeah. Then you substitute 2k for x and 3k for y into the expression, 3x plus 2y, 2x plus 5y. The cakes will eventually cancel out.
And either way you do it.
You get the same answer, 12.1. It just shows there's often more than one path in math.
True. But that leads to a really important warning the book gives.
Yes, this trips people up sometimes.
Just because xy is 2.3, it doesn't mean x has to be 2 and y has to be 3.
Exactly. They use that age example, right?
Yeah.
Mohit is 15, Rahul is 24.
Yeah.
Their age ratio is 15.24. If you simplify that, divide both by 3, you get 5.8.
Right, for that point, yeah.
But obviously, Mohit isn't 5 years old and Rahul isn't 8.
Yeah.
The ratio just tells you the proportion. There's a hidden scaling factor. In this case, it was 3.
That's such a good clarification. The ratio is the relationship, not the actual numbers themselves.
Precisely. That k we used, that represents that possible scaling factor. X is some multiple of 2. Y is the same multiple of 3.
Makes perfect sense now. Okay, more examples. Finding 5a plus 8b, 6a, 7b when ab is 5.3. Same principle, substitute or use k, and it comes out 49.9.
Straightforward application.
And then word problems. Love these.
Well, they show the application.
Two numbers are in the ratio 3.5. Add 8 to both numbers, and the new ratio is 2.3. Find the numbers.
So you set it up algebraically. Let the numbers be 3k and 5k.
Right.
Then 3k plus 8 divided by 5k plus 8 must equal 23.
Okay, then solve for k.
Solve for k. You find k is 8. So the original numbers were 3 times 8, which is 24, and 5 times 8, which is 40.
24 and 40. Nice.
Oh, yeah.
It really shows how ratios model these situations.
Absolutely. Translating words into the math is the key skill.
Then there's one about adding something to 8.15 to make it 3.5. Works out you need to add 2.5.
Yeah, similar setup. 8 plus x, 15 plus x equals 35. Solve for x.
But then they did something cool. They generalized it.
Ah, the formula.
Yeah. Finding the number x you need to subtract from AB to make it CD.
Yeah.
And there's a formula. X, B, C, A, C, D.
That's the beauty of math sometimes. Find a pattern, create a formula, save yourself work next time. It shows the underlying structure.
Definitely powerful. Okay, shifting gears slightly. A work rate problem.
Always fun.
The ratio of work done by x3 men in 2x plus 1 days compared to the work done by 2x plus 1 man in x plus 4 days is 3.10. Find x.
Okay, so work is often proportional to the number of workers times the time they work.
Right, so the ratio is x3, 2x plus 1, 2x plus 1, x plus 4 equals 3.10.
Notice the 2x plus 1 term appears on both sides of the ratio.
Oh, so it cancels out.
It does, assuming it's not 0. So you're left with x through x plus 4 equals 3.10. Much simpler.
Much simpler. Cross multiply again. 10 by 3 equals 3x plus 4.
Yep. Solve that. You get 10 by 30 equals 3x plus 12. Rearrange. 7x, 42.
So x6.
X equals 6. And the book makes a good point. Sometimes algebra might give you another solution, like a negative one here. But you have to check if it makes sense in the context.
Right. You can't have, like, 6, 3, 3 men. But if x was, say, 1, you'd have 1 to 3 and equals 2 men. Doesn't make sense.
Exactly. Math gives solutions. Context gives meaning.
Good point. Okay, moving on. Increase and decrease in ratio.
Right. If something changes in the ratio AB...
The new amount is b times the old amount.
Yes. So if B is bigger than A, it's an increase. If B is smaller, it's a decrease.
Example, airliner fare goes up in the ratio of 5.7. Original fare was 10.15.
So the new fare is 75 times 10.15.
Which works out to 14.21.
And the increase itself is just the difference. 14.21 minus 10.15, which is 4.06.
Straightforward scaling. Then a trickier one. Officers and soldiers.
Ah, yes, the battle example.
Start with a ratio of officers to soldiers, 3.31. Then there's a battle. 6 officers and 22 soldiers are killed. The new ratio is 1.13. Find the original numbers.
This one needs setting up carefully. Let the original numbers be 3K officers and 31K soldiers.
Yeah.
After the battle, you have 3K 6 officers and 31K 22 soldiers.
Right, and the ratio of these new numbers is 1.13.
Exactly. So 3K 6, 31K 22 equals 113.
Another equation to solve for k, cross multiply again.
That's a bit more involved, but yeah. 13, 3K 6 equals 131K 22.
So 39K 78 equals 31K 22.
Rearrange. 8K equals 56.
K equals 7.
K is 7. So the original number of officers was 3K. It was 37 equals 21.
And soldiers, 31K equals 31.7 equals 217.
21 officers, 217 soldiers originally. It shows how ratios help track changes in group composition.
It really does. Okay, some special cases mentioned. If you have AB plus C, BC plus A equals CA plus B. Interesting setup.
Yeah, a bit abstract, but leads to cool results.
If a plus B plus C happens to be 0,
then each of those fractions, each ratio equals -1.
How does that work?
Well, if a plus B plus C, then B plus C, A plus A, so the first ratio becomes A, which is -1. Same logic applies to the others.
Ah, neat. But if a plus B plus C is not 0,
then each of those equal ratios is equal to 12.
1/2. Why?
There's a property of equal ratios. If X by equals CZ, then each ratio is also equal to A plus B plus C, X plus Y plus C. Sum of numerators over sum of denominators.
Okay.
So here, each ratio equals A plus B plus C, B plus C plus C plus A plus A plus A plus B.
The denominator is B plus C plus C plus A plus B. That's 2A plus 2B plus 2C.
Exactly. So you have A plus B plus C, 2A plus 2B plus 2C. Factor out the 2 downstairs.
C plus B plus C, 2A plus B plus C.
And since A plus B plus C isn't 0, you can cancel that term.
Leaving 12. Wow, that's elegant.
It is, isn't it? Shows the power of these properties.
Okay, next distinction. Commensurable versus incommensurable quantities.
Right. Commensurable basically means their ratio can be written as a ratio of 2 whole numbers, 2 integers.
Like the example 2 and 13 compared to 3 and 12, that's 73 to 72.
Yeah. And if you handle that ratio of fractions, it simplifies nicely to 2.3, an integer ratio.
So they share a common measure, essentially.
You could find some unit, maybe small, that fits perfectly into both a whole number of times.
But incommensurable.
That's when the ratio cannot be expressed as integers. The classic is the diagonal of a square to its side that's square root of 2 to 1.
Right. Siggy 2 is irrational.
Exactly. The book gives 3 and 5 as another example. You just can't find two integers whose ratio perfectly equals 3, 5.
This was apparently a big deal for the ancient Greeks.
Oh, huge. Discovering incommensurability, that not everything could be measured by integer ratios, fundamentally changed their understanding of numbers and geometry, led to irrational numbers.
Fascinating bit of history there. Okay, now combining ratios, composition. First is compound ratio.
Simple idea. Just multiply ratios together, antecedent times antecedent, consequent times consequent.
So if you have, say, 3 by 2b, 2 meter n, and 4 by 0.3y.
The compound ratio is 3a, 2 meter, 4x, 2b, n, 3y.
Which simplifies. 24mx, 6b narni, divide by 6.
4mx, bn.
Yep. It's the net effect of applying several ratios one after another.
We get these special compound ratios. Duplicate ratio.
That's just compounding a ratio with itself, so AB becomes A dot B out.
Like squaring it. Example, duplicate of 2.3 is 4.9. Right. Think area. If you double the sides of a square, ratio 2.1, the area increases by 2.1 pascal, which is 4.1.
Ah, connects to geometry, so triplicate ratio must be.
Cubing it. AB becomes A dot BU.
Triplicate of 2.3 is 8.27.
And that relates to volume. Double the size of a cube, the volume increases by 2.1 number, which is 8.1.
Okay, makes sense. Then we go the other way. Subduplicate ratio.
Square root.
Subduplicate of 9.16 is 9.16.
3.4.
It's like going from an area ratio back to a length ratio.
And subtriplicate.
Cube root.
Subtriplicate of 27.64 is 227, Pat. 3.4 again.
Going from a volume ratio back to a length ratio. Inverse of triplicate.
Got it. And finally, reciprocal ratio.
Easiest one. Just flip it. AB becomes BA, or 1A, 1B.
Reciprocal of 3.5 is 5.3. Just the inverse comparison.
Exactly.
And the book wraps the ratio section with a combined example. Find the compound ratio of duplicate of 5.6, reciprocal of 25.42, and subtriplicate of 216.343.
Okay, let's break that down. Duplicate of 5.6 is
25.36.
Reciprocal of 25.42 is
42.25. And subtriplicate of 216.343. Cube roots.
Cube root of 216 is 6. Cube root of 343 is 7, so 6.7.
Right. Now compound these. 25.36, 42.25, 6.7. Multiply the first terms. 25, 42, 6. Multiply the second terms. 36, 25, 7.
Okay, 25, 42, 6. 36, 25, 7.
It's messy.
But look for cancellations. There's a 25 on both sides. Gone.
Yeah. Nice. So 42, 6, 36, 7.
And 42 is 6, 7. So 6, 7, 36, 7. There's a 7 on both sides. Gone.
Okay. 6, 36. 36, 36. 36.
Which simplifies too.
1.1.
Wow.
All that work for 1.1.
It's a great example of how seemingly complex combinations can simplify dramatically. Everything canceled out.
A definition. 4 non-zero quantities, A, B, C, D, are in proportion if the ratio AB equals the ratio CD.
Written A, B, C, D, or sometimes A, B, C, D. The double colon means is proportional to...
And terminology, A and D are the extremes.
The outer
terms are the means.
The inner terms.
And the fundamental property.
Product of extremes equals product of means. So add BCC. Add ADBC. Comes right from AB equals CDD. Just cross multiply. Super useful.
Very useful for solving problems.
And if ABCD, then D gets a special name. The fourth, proportional to A, B, and C.
Yes, it's the value that completes the proportion.
Important note on units again. Within each ratio, units must match. A and B same kind, C and D same kind. But the two ratios don't need the same kind of units overall.
Exactly. The example was 5 kilograms, 15 kilograms equals 75 euro, 225.
Kilograms on the left, rupees on the right, but...
Both ratios simplify to 1.3. The numerical relationship holds. The dimensionless ratios are equal. That's the proportion.
Got it. Then there's continued proportion.
This is for 3 quantities, A, B, C. They're in continued proportion if AB equal BC.
The middle term B is repeated.
Yes, and B is called the mean proportional between A and C.
Mean proportional.
That's
okay,
right.
And C is the third proportional to A and B.
Right. Since A, B, B is B, you can find C if you know A and B, or find B if you know A and C. B, B's AC, so B equals...
And this can chain together. A, B, C, E, C, D, E, C, D, D.
Exactly. A whole sequence linked by these equal ratios. It implies a constant scaling factor between consecutive terms.
Okay, examples for proportion. Find the fourth proportional to 3, 6, and 4.5.
So we need 3.6, 4.5. The product of means equals extremes. 3 equals 6, 4.5.
6 times 4.5 is 27, so 3 equals 27.
D9?
Simple enough. Find the mean proportional between 6.25 and 0.16.
We need b such that 6.25, b equals b.16. So b bar equals 6.25, 0.16.
6.25 times 0.16. That's exactly 1.
It is. So b bottle of 1, meaning b must be
1 or NACS 1, but usually we take the positive mean. So 1.
So usually the positive, yeah.
Let's find the third proportional to 1.2 and 1.8.
So we need c, where 1.2, 0.2, product of extremes, product of means. 1.2c was 1.8.
1.8 squared is 3.24. So 1.24 by 1.2 gives you 2.7.
C at 2.7. Okay. These really just lock in the definitions.
They do. Practice the mechanics.
Last one. A, 2, 10, and B are in continued proportion. Find A and B.
Continued means the ratios link up. A2 equals 210 equals 10B.
So we have two separate equations here. First, A2 equals 210.
Right. Cross multiply 10A equals 4. So A equals 410 or 0.4. Okay, A equals 0.4. And the second equation is 22010 equals 10B.
Cross multiply again. 2B equals 100.
So B equals 50.
There you go.
Yeah.
A is 0.4, B is 50. Uses the chain property.
That nicely ties continued proportion together. Okay, let's try and summarize this deep dive.
Sounds good.
We've really dug into ratios first, comparing quantities, same kind, same units, key properties, unitless, order matters, simplification.
And all those ways to combine them. Compound, duplicate for squares, triplicate for cubes, then the roots with subduplicate and subtriplicate, and the simple reciprocal.
Right. Then we move to proportion, the equality of two ratios, A, B, C, C, Z. The big rule, product of extremes equals product of means.
And distinguish that from continued proportion, AB equals BC, introducing the mean proportional and third proportional concepts.
Fundamentally, it feels like these are just core tools for comparison and scaling.
Absolutely. When you step back, you see how these, well, seemingly simple ideas underpin so much quantitative reasoning. Cooking, maps, engineering, finance, science. It's all built on understanding these relationships.
It really is a fundamental language. Which leads us to a final thought for you listening.
Yeah.
Think about how this basic idea, ratio, really forms the foundation for complex concepts everywhere. Adjusting a recipe, reading a scale drawing, understanding financial ratios like debt to equity, or even scientific concentrations. How might getting a really solid grasp of ratios and proportions actually empower you to analyze things differently? To see the world around you maybe with a sharper quantitative eye?
What everyday things could be understood better just through this lens of comparison and proportion?
Definitely something to ponder. Thanks for taking this deep dive with us.